Okay, and we're starting. So, last time, we found a solution to the rate problem. It's called the derivative. Okay. So, for a function f of x, its derivative, if it exists, and I'll probably talk about that presently, is given by what is it given by? How do we define the derivative? Yeah.
The limit has h of f of x plus h minus f of x over h.
That limit, if it exists, gives us what we call the derivative. It has many interpretations. One thing you can remember, this is the rate of change of f at x. It is the slope of f at x. It is, more specifically, the slope of the tangent line to f at x. You can also think of it in terms of a speed or a rate, how fast f is changing with respect to x. So this was called the derivative, and it was meant to solve the rate problem. Whenever it exists, we can actually use it to solve the rate problem. Assuming we can define a function and we can find this limit, I can talk about how fast the dependent variable is moving with respect to the independent variable. One thing we know that we hopefully recall, I mean it's been a long time so prior to the is that we found this by approximating f with a straight line. This, by the way, suggests when a derivative let's actually talk about that right now. I think I probably spoke about it. I think I plan to speak about it a little while from now, but I don't know, the moon strikes, so let me just get it out of the way. Talk about the existence of the derivative. So remember, it is a limit, so it might not exist. And I want you to notice that intuitively, based on the above the derivative of f at a point exists if f is approximately linear at that point. Meaning, if I zoom in, the function starts to look like a straight line. It starts to, you start to have the situation where the more I zoom in, the more it actually looks linear. So I can approximate it with a linear function. Now, there are cases where we can't actually do this. So let's actually talk about an important one. Sharp corners and cusps. Cusp is another fancy name for a sharp corner that where the inflection is. For us, just think of a cusp as a fancy word for sharp corner. I'll describe to you more what those means. Notice that if we have a sharp corner, something that looks like that, that's what I like a cusp. Then, and I wanted to actually take a derivative at this point, at the sharp corner. What you would notice is that, well, for one, what would be the tangent line to this curve at that sharp corner? One, we know that the tangent line should actually touch the curve. There's a line that touches the curve. I can draw another line that touches the curve at that point. I can draw another line that touches the curve at that point. I can draw another line that touches the curve at that point. I can draw another line that touches the curve at that point. I can find tons of lines that touch the curve. Infinitely many, in fact. But none will approximate the curve. Because no matter how much you zoom in, a sharp corner is never going to look flat. Right? It's never going to be the case where you're zooming in and, oh yeah, I see it flattening out now. No, it's a sharp corner. It's always going to be sharp. There's always going to be one point in that location and no points beside it. It will always look like a sharp corner, no matter how much you zoom in. Now, for a concrete example of seeing why this is an issue, there's a very, very typical example I can talk about. Is y equals the absolute value of x at x equals 0. So you might remember what that looks like. You should. That's a V-shaped thing. So you remember that the equation on this side is going to be y equals x, and the equation on that side is going to be y equals minus x. And then x equals, the function equals 0 and x equals 0. This gives us the absolute value function. Now, what actually happens if I try to find, let's say I call this f of x, and we ask the question, what is f prime evaluated at 0? I.e., what is the slope at 0? Then we simply use the derivative. We know f prime of 0 is just going to be the limit as h approaches 0 of f of 0 plus h minus f of 0 over h. This is by me using the derivative formula. If you start to plug that in for your absolute value function, this is the absolute value of 0 plus h minus the absolute value of 0 all over h. This is going to be, of course, limit as h approaches 0, the absolute value of h over h. Because absolute value of 0 is 0, 0 plus h is just h. And what is this limit? I've actually discussed very similar limits before. In fact, I think I discussed this exact one before. What happened with this guy? What is the limit as h approaches 0? Huh? What? It does not exist. Why? Right, because the absolute value splits it into two parts. It gives you h over h, the limit of that if your h is greater than 0, and it gives you minus h over h if h is less than 0. And so this limit is kind of trying to find that function. And of course, the limit's not going to exist here because the left doesn't match up with the right. So this does not exist. i.e., the derivative does not exist at 0. So that's a very computational example, but pretty much any sharp corner is going to behave the same way. You're measuring the slope coming from one side, it's not going to be equal to you measuring the slope coming from the other side. The derivative limit, therefore, will not agree on the left and the right, and you will have your derivative not existing. Intuitively, this is because you zoom into a sharp corner, it'll never look like a straight line. Computationally, you should be able to figure that out as well if you know the formula for the sharp corner. But just know in general, can't find derivatives at sharp corners. That's something you should know. The derivative of a function will not exist at any point where the function is jagged. And you can have very jagged functions. We're not going to look at any functions like that, but there are functions where they're continuous everywhere, but they're not differentiable anywhere because they're just like static, very jagged. Every point on this function is like a sharp corner. Any of you who are math majors and you start to do advanced calculus, you start to look at crazy functions like that, but for now I'm going to avoid them. But if I give you a function with just a few sharp corners, I expect you to realize that at those sharp corners, the derivative is not going to work out. The second place where the derivative is not going to work out, f prime does not exist where f is discontinuous. Again, if you have like a hole or you have like a jump or something like that, we can't draw a tangent line at these points because the points doesn't even exist. Because there are gaps. Gaps won't look like a straight line no matter how much you zoom in. It'll always be a gap. So if we're not continuous, the derivative won't exist. If we're at a sharp corner, the derivative won't exist. There's a third situation which is kind of weird. F prime does not exist where f has a vertical tangent. Now there are doesn't even have to be too weird. I can just create a function by, say, stitching two semicircles together, like one semicircle that does that. Then take the bottom half of another semicircle. And I can create a function like that. What you'll notice here is that the slope of the curve is approaching a vertical line. It's also approaching a vertical line from here. It turns out that a tangent line does actually exist at weird things like that, but the tangent line would be a vertical line passing through that point. If you zoom into this location, it will start to actually seem to flatten out to look almost like a vertical line. The problem with vertical lines is they don't have slopes, right? You can't write a vertical line in the form y equals mx plus b. There's no m to speak of. So this is a vertical tangent line. Slope does not exist. Therefore, the derivative does not exist. Now, yes, functions do need to pass the vertical line test, but we are in a situation here where the function literally goes vertical for one point. So it will pass the vertical line test. It passes it too close for comfort. So you can have situations where, yes, the function is continuous, and yes, technically you can get a tangent line, but the tangent line is vertical, and so the derivative won't exist there. There's no slope. So these are three situations in which your derivative does not exist. So that limit, it's very important. It solves a very big problem, a rate problem, but it's not all powerful. There are cases where it's rendered helpless. We can't find the derivative. Those are the three main situations. So if I give you a graph, like a picture of a graph, I could ask you, where is this going to be differentiable? And you'd be able to point out any problems with the graph. Oh, there's a gap here, there's a sharp corner here, it's not going to work there. You should be able to actually look at the graph and tell me that. And of course, if I give you the formula for a function, you should be able to try to compute the derivative using the limit definition, and you'd be able to tell me if it doesn't work out. Okay. More facts. Okay, so that's trying to be cool, but you can't joke like that. People are going to start thinking I don't know how to spell facts. More facts. Here is something that is important. It's actually very important. Let's call it a theorem. If f is differentiable, meaning the derivative limit exists, then f is continuous. Differentiability implies continuity. This is a very important idea. Once you know that you can find a derivative somewhere, the function is automatically continuous there. You don't have to actually check the continuity. That is extremely useful in many situations. And so f prime exists implies that f is continuous. At least at the points where the derivative exists. That's a very important fact, and I'm going to be proving some things for you where I'm going to use that fact. Let's do a short proof. Suppose f prime of x exists at x equals 8, then that means the limit as I want to use another version of the derivative limit just because it's just easier with the notation here. I want to use that version. Let me just do a little side note here. A lot of times I use the limit as h approaches 0 f of x plus h minus f of x over h, but sometimes it's just nicer to use this one. So if you look at some curve, remember how we actually found the derivative. If I call this x and I call this point x plus h, and I call that point, this is f of x plus h, and this is f of x, then the slope of secant is going to be equal to f of x plus h minus f of x over h. Right? But by renaming, okay, I can have the same situation, but instead I can call this like a, and call that like x, and this would be f of a, and that would be f of x, and exactly the same scenario, slope of secant is going to be equal to f of x minus f of a over x minus a. Rise over rho. It's the same idea. So these two are equivalent. There are sometimes when we'll use this one though, and I'll talk more about that when we get to it. We're going to talk about average rate of change and things like that. And this form is nicer for applications like that. And the notation is going to be nicer for me to use that version here. So that's what I'm doing. So this means that the limit of this expression, which is the slope of the secant, as the distance between x and a go to 0, equals f prime of a, which is just a real number. Then, let's say if I look at the limit as x approaches a of f of x minus f of a. Okay, let's say I wanted to find that limit. This is going to be equal to the limit as x approaches a. I'm going to do this thing where I multiply and divide by something convenient because it's convenient. I can multiply by x minus a, and then I can divide by x minus a as well. Multiply and divide by x minus a. We have the limit property. Now, this is equal to the limit as x approaches a of x minus a times the limit as x approaches a of f of x minus f of a over x minus a. We know that limits distribute across products, so we can use that property. What's the limit of this as x gets close to a? 0. What's the limit of this as x gets close to a? F prime. Right? We're assuming this exists. So in other words, I get 0. So what that means is that the limit as x approaches a of f of x minus f of a is 0. But that means that the limit as x approaches a of f of x, distributing the limit across the sum, because limits can do that, of f of a equals 0. This means that the limit as x approaches a of f of x equals minus. The limit as you approach a constant is just going to be the constant, equals 0. And so you end up with, finally, the limit as x approaches a of f of x equals f of a. And that means it's continuous at a. Don't need to know that proof, I just want to show you that if you assume something is differentiable, that this limit exists, then automatically you'll have the limit as x approaches a of f of x equals f of a, which by definition means f is continuous at a. So if we can find the derivative at a, f is continuous at a automatically. multiply and dividing trick, you see that all the time. I'm going to be using that several times. So that's important. It's important for you to know the statement. You don't necessarily have to know the proof. I just thought I'd show you. Eventually, some of you will need to know proofs. And it's important to know the converse is not true. The converse of an implication is just a statement in the opposite direction. A lot of mistakes happen because people always assume the converse is true once you make a statement in a certain order. Meaning, if f is continuous at A, does it mean that f prime exists at A? And the answer is no. This is not true. Okay? If f prime exists, it's continuous. But if it's continuous, it does not mean that f prime exists. We actually did an example here. Y equals absolute value of x. Right? I just showed you. That's continuous at x equals 0. But f prime of 0 does not exist. So you need to be continuous to have a shot at the derivative existing, but you can be continuous and the derivative still doesn't exist. You have to be a nice kind of continuous. You have to be a very smooth kind of continuous. The kind of continuous that when you zoom in, it starts to look flattened out. It's a very gentle kind of continuous. If you're too jagged and continuous, that's a problem. So, yeah, you can differentiate something if it's approximately linear at that point. This implies that you can't differentiate something where there's a sharp corner. You can't differentiate something where it's not continuous. You can't differentiate something when there's a vertical tangent line. It also means that if you're differentiable, if you can find the derivative, the function is automatically continuous at that point. However, it's possible to be continuous, but you can't find the derivative. Absolute value of x is a nice example. Okay. Here's another fact, which I will, if all goes according to plan, I'll use later today to show you something very important. The plan today is to end with one of the most important derivative theorems out there. So let's call this, I don't want to call it a theorem, because it's not like big and monumental enough to be called a theorem. Not even a lemma. Let's just call it a fact. Let's call it fact 2. Okay. So for the rest of this lecture, fact 2 is going to be this fact that I'm talking about here. And here's what it says. If f is continuous at x equals a, then as x minus a approaches 0, I will call this the change in x. Call this delta x. Then the difference between f of x and f of a will approach 0, and this I will call the change in f. Now that's it's just a nice fact that follows very easily from the definition of continuity. So this basically says we know that the limit as x approaches a of x minus a is going to be 0. So as x is approaching a, the distance function will, the distance between x and a will be 0. And we know that the limit as x approaches a of f of x equals f of a, since f is continuous. This means that the limit, move it to the other side, will be 0. This automatically means the limit of A equals 0, and this automatically means the limit as x approaches A of your delta f equals 0. So pretty much for a continuous function, let's let it be whatever. Let's make this a little more sloped so you can see it. If we're looking at this point, then as here's your f of x, here's your f of a. Basically, you can see as the x's get close together, the y's will get close together when continuity is happening. So basically what that means, as the change in x gets small, the change in y's will automatically also get small. And that's just me just rewriting the definition of continuity. You can notice that actually works. So it's a very simple thing to say. You might not think it's very important, but later on I'm going to use this thought to show something very important, to help me show you something very important. Now, I have one more proof to show you, but we're not going to do that just now. We're going to take a break from all this heady stuff and just do some more computations. Everyone loves computations. Also last time, we found if f of x is equal to x squared, then what was the derivative of x squared? 2x. This is what we saw last time. We set up the limit as h approaches 0, f of x plus h minus f of x all over h. We did our mumbo jumbo, we canceled the h in the bottom, we plugged in h equals 0, and 2x popped out. This can be expressed as saying dx of x squared equals 2x. Okay? So you can just know that. Well, you should actually memorize that, I would say. So it probably does deserve a box around it. Right? So this means this is something that we can compute. Right? I give you a function y equals x squared, and I ask you what is the formula for the derivative. And you can tell me, oh, it's 2x. Now what that means is that this guy gives a formula for the slope of the tangent line. Okay. So if I ask you, what is the slope of the tangent line to y equals x squared when x equals 3? The answer is going to be 6. What is the slope of the tangent line to y equals x squared when x is 5? The answer is going to be 10. What is the slope of the tangent line to y equals x squared when x equals minus 3? The answer is going to be minus 6, right? Anytime someone asks you about the slope of the tangent line to a point at x squared, you can figure that out by using the function 2x. We call 2x the derivative of the function x squared, and it works as a formula. Now I know whenever I want to find the slope of x squared at a point, I can use the function 2x as a formula to evaluate what that slope is. Now here's the thing. It's important to be able to do this in general. Now, I'm not going to convince you of that today, but just know in general, it's important to be able to do this in general. That's what we're going to be spending the next few weeks on. Really figuring out how to find derivatives of various functions. And we're going to start out using the limit, but eventually, as you'll see, it's going to be very cumbersome to use the limit. So what we're going to start to do is derive certain formulas where I can know that certain kinds of functions that look certain kinds of ways, I can use these very shortcut formulas to get to the derivative a lot quicker without me having to go through the whole limit definition. But until then, all we know is the limit definition, so let's actually get some practice using it, because you will for sure be tested on using the limit definition to compute a derivative. So let's get some practice in there. It's on pretty much every final, and I'm going to put it on test 1. So you should know how to find things using the derivative definition, the limit definition of the derivative. So we'll learn to do this easier later, but for now, we'll use the limit definition. I wonder if in med school they made the doctors write on chalkboards. That's probably something. Because my handwriting gets worse when I write on the chalkboard. It's like hard. Doctors' handwriting, they're really bad. Maybe they have to like write a lot of stuff on chalkboards all the time. Something to think about. Let's do some examples. Find f prime for the following. A. Let's find f prime if f of x equals c, where I'm just talking about a constant. B. What about if f of x equals c times x? Again, c, a constant. What about if f of x equals the square root of x? What about if f of x equals 1 over x? What about if f of x equals, let's do the sine of x. Let's actually derive the derivatives for these functions. So like I said, it's very important that you are able to do this from the definition. In order to do that, you need to know the definition and know how to apply it. And it just comes down to actually computing a limit. A. What is f prime? What is f prime in general? Yeah? Yeah, go.
The limit as h equals 0 of f of x plus h minus f of x.
Now for this function, f of x equals c, what is f of x plus h? It's still just c, right? There's no x to plug in. What is f of x? Well, it's c. So that's just the limit as h approaches 0 of, well, 0. That's 0. Turns out the derivative of any constant is going to be 0. Now, on one hand, that should be obvious because if I look at y equals a constant, what does its graph look like? It's just a horizontal line passing through c. The slope of a horizontal line is 0. So it makes all the sense in the world that the derivative of a constant should be 0, because the derivative is just trying to find the slope of the tangent line. I can make this statement in general. I can say d dx of a constant is 0 regardless of the constant. That's just something we know now. The derivative of a constant is 0. It doesn't matter what the constant is. The derivative of 5 is 0. The derivative of 7 is 0. The derivative of e is 0. The derivative of pi is 0. The derivative of 17.9 over radical 2 plus pi e squared is 0. It does not matter what the constant looks like, the derivative is going to be 0. The derivative of a constant is 0. This is just something we know now, right? And this is the proof for it. No matter what the constant is, f of x plus h and f of x are going to be the same thing. The derivative will be 0. that takes care of this situation. And this is the proof, but now we know that as a shortcut. If I'm looking at a constant, the derivative of that constant is 0. Let's do a constant times x. If I have a constant times x, what is the derivative of that? What is f prime of x? Limit as h approaches 0, f of x plus h minus f of x all over h. Did I actually ask that on the quiz? Yes, I did. Okay, that's good. Because that's definitely something I intended to ask on the quiz. I wrote the quiz a long time ago. I forgot what I actually wrote on it. That definition you must know. I will ask you to regurgitate the definition of the derivative on the first test for sure. If I ask you what is a derivative in general, you should write that down. The entire equation, both sides of the equation. Okay, so that is what a derivative is. Now, if my function is c times x, what is f of x plus h? Yeah.
C times x plus h.
C times x plus h. Just go in and replace all x's with x plus h. Your f of x is of course going to be c times x. Right? How do I find this limit? You distribute the c. This will kill that one. And then afterwards, because I only have this, the h's will cancel. And so I would have the limit as h approaches 0 of c. Well, that's just c. In other words, I can say that the derivative of a constant times x is the constant. Now that should also make a lot of sense because y equals cx is just a line through the origin and it has slope c, right? mx plus b, right? The m is like the c, the b is like the 0. The slope of the line with slope c is c, right? So the slope of cx is going to be c. The slope of a constant times x is always going to be just a constant. In particular, the derivative of x is what? It's going to be 1, because there's a 1 here. That's also something we know now. Derivative of x is 1. And in general, the derivative of any constant times x is going to be the constant. So the derivative of 5x is just 5. The derivative of 7x is just 7. The derivative of pi x is just pi. The derivative of radical 2 times x is just radical 2. The derivative of a constant times x is just the constant. The derivative of x is 1. Right? That's something we know now. Right? That's something we know automatically. That's another thing that we just know. But that's the proof. Actually, to prove that the derivative of x is 1, you would actually go through and you do this, where your c would be the number 1. But that makes a lot of sense. These two make a lot of sense because that's just a horizontal line, the slope is just 0. This makes a lot of sense because the slope is c of the line, so the derivative is just c because the derivative is the slope. This one is a lot less obvious if you don't never seen a derivative before. What the heck is the slope of radical x? Let's figure it out. Radical x is weird because now the slope is a function. How do I know? Because it changed. The slope over here is not the same as the slope over there. So the slope is not going to just be a number. It'll be something that's changing. The slope will be a function in and of itself. What function would it actually be? Well, What is f prime of x? Limit as h approaches 0. Write it down every time so that it's burned into your brain. That's the derivative. Now, if my f of x is radical x, what is f of x plus h? Yeah.
It's radical x plus h minus.
Like this?
No, it's radical x plus h, but like, yeah, no.
I did that because that was a common mistake. Don't do that. It's all of that. The entire x gets replaced by x plus h. Minus f of x, well, that's just radical x all over h. How do I compute this limit?
How? You would multiply by the squares.
Multiply by the conjugate?
Yeah, the conjugate.
Yeah, so?
And you would get h.
Well, what is the conjugate?
Oh, it is radical x plus h plus radical x. And that's going to also go in the denominator.
Right, you have to multiply and divide by the same thing, so you're not changing the value.
And then
What happens in the top now is going to be difference of squares, right? I have a minus b times a plus b, so the result is going to be a squared minus b squared. In the bottom, I would have h radical x plus h plus radical x. Never distribute the denominator of a fraction. So it's also something that students seem to do for some reason. I don't know why you do it. Never expand the denominator. Leave it in factor form. So don't distribute this h all over the place. Okay. Now what's going to happen is your x's are going to kill each other, x minus x. And then I'll just have an h in the top and a product in the bottom. So then eventually the h's would also cancel. And then so I'm going to be left with the limit as h approaches 0 of 1 over radical x plus h plus radical x. What is that? How do I find that? Yeah.
h is 0.
Now you just plug in h equals 0. Remember, the point of finding the limit is you try to plug in. You can't plug in, simplify to a point where you can plug in. Now, that is just going to mean you're left with radical x plus radical x, or 1 over 2 radical x. Now, as long as your x is not 0, it's larger than 0, that will be defined. Now, we need our x to be larger than 0 anyway, but notice that at this point, the derivative does not exist. However, for anything after that point, this is how you find the derivative. And now, that is just something we know now. The derivative of the square root of x is 1 over 2 square root of x. And that's the proof. Let's keep going. I know I'm flying through this, but by now we all know how to compute limits very well, and it's just us applying a formula while computing a limit. That should be pretty standard stuff you can almost do in your sleep. And I asked you to do on the quiz today, so we'll see how you guys did. Let's do D. Again, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Now I get it right now, some of you are rolling your eyes, but I guarantee there will be people who get that wrong on test 1. See how many times I'm repeating it? Guaranteed, I'll bet you any money. There's someone who's not going to know how to write that down on test 1. Know the definition of the limit. Every time I teach Calc 1, I write this formula down so many times. And every time I teach Calc 1 and test 1, I ask them, what's the definition of the derivative? And every time someone gets it wrong. I've never given a Calc 1 test where everyone got that problem right. I don't know. I can't explain it. I just know it happens. Now we are looking at 1 over x. What is f of x plus h for 1 over x? Yeah.
1 over x plus h.
Replace all x's with x plus h. That's your f of x all over h. How do I find the limit of that? This is actually very similar to the quiz problem. There was a point where you had to do something like this. I thought I asked you like a constant plus 1 over x or something like that. The constants would automatically kill each other. You'd be left over with this. How did you proceed? Yeah. What? Okay. And then you looked at this as h over 1 and then the keep change flip thing? Yeah.
It becomes x minus parentheses x plus h.
Yes.
Or x times x plus h.
Yeah. And then what did you do?
And then simplify.
And then what?
Simplify.
Okay. How did you simplify? Huh? So that's doable, and hopefully you continued in the right way. But the easiest way to simplify a complex fraction is to multiply and divide by the LCD. That's what I would have done. You take this guy, distribute. In the first case, the x plus h cancels, and you'd be left with x, minus in the second case, the x's cancel, and you'd be left with x plus h. At this point, a lot of students would forget the parentheses. Over hx times x plus h. At this point, the x's will cancel. I'll be left with minus h on the top over hx times x plus h. Now the h's would cancel. And I'd be left with minus 1 over what? Now I can plug in h equals 0 without making the denominator identically 0. I will be left over with x times x, which is x squared. And so that's now something we also know. The derivative of 1 over x is minus 1 over x squared. You should know that automatically. Now, of course, x equals 0 is a problem there, but it was even a problem for the original function. This doesn't even exist as 0. So I had no hope of being able to find the derivative at that point anyway. But as long as our x is not 0, this gives us a formula for the slope to that curve at any value x. Okay, someone tell me how to do E. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, what is f of x plus h? Yeah.
Sine of x plus h.
How do I complete that limit? Yep.
Like sine of x plus h.
As?
Sine of x cosine of h plus cosine of x sine of h.
Correct. That is the addition formula for sine. That is what we will apply here. Yes, I expect you to know the addition formula for sine. I expect you to know all your trick. Every trick that anyone has taught in any pre-calc class ever, I expect you to know it. Sine of A plus B is sine A cosine B plus sine B cosine A. So this becomes sine X cosine H plus sine H cosine X minus sine X all over H. Now, that's going to be now, if I look here, there's a sine X and a sine X in common here. Probably what I want to do is group those and maybe split the fractions. That's going to be the nice way to do it. So here I would have sine X times cosine of H minus 1 over H. Plus, here I would have sine of H cosine of X over H. Okay, what's the first part, limit of this? What's the limit of this? Yeah. 0. You guys are taking way too long. That's something you should know automatically. The limit of cosine x minus 1 over x as x goes to 0 is 0. That's a special trig limit. What's the limit of this? Yeah? Cosine of x. Why? Because sine h over h as h goes to 0 is 1. That's also a special trig limit. You know that automatically. So we have 0 plus 1 times cosine. Cosine. In other words, the derivative of the sine function is the cosine function. That is something that we know now. We can similarly derive the derivative of cosine. You will find that if you go through this process for the cosine function, the answer is, who knows? Yeah? Negative sine x. Details left to the reader. But I just showed you how to find sine. Finding cosine is going to be very similar. So, we know derivative of any constant is 0. Derivative of any constant times x is the constant. The derivative of radical x is 1 over 2 radical x. The derivative of 1 over x is minus 1 over x squared. Derivative of sine is cosine. Derivative of cosine is minus sine of x. These are all things we know now. We know them in our sleep. You should also know how to actually compute a derivative using the limit definition. It is for sure coming up on test 1, and it is 99.9% sure to come up on the uniform final at the end of the semester. Okay, so we know all that. Here are some other useful things to know. Let's talk about the algebraic properties of the derivative. There are two main properties that I expect you to know for a derivative. Let f of x and g of x be differentiable functions. C be a constant. Then, here's one property of the derivative. You can factor constants outside of it. Meaning, if I wanted to find the derivative of a constant times the function f of x, this is going to be a constant times the derivative of the function f of x. Constants can factor outside of derivatives. This is a very important property that will be very useful. Why? Well, if I take the derivative of a constant times f of x, well, that's just the limit as h approaches 0 of c times f of x plus h minus c times f of x all over h. Limits we know has this rule. You can factor out common factors from a limit. So you can actually factor out the c and put it outside the limit. And then this guy here is just the derivative. And this guy is just the c that's standing there. So the derivative of a constant times a function is just the constant times the derivative of the function. This is a very important property. So, example, if I ask you, what is the derivative of 7 over x? Well, just realize that's 7 times the derivative of 1 over x. This is just 7 times minus 1 over x squared, which is minus 7 over x squared. Eventually, I'll expect you to jump from this point to that point, but I'm showing you why you can go from this point to that point. If I needed to and this is going to work for any of them. So if I wanted to, another example, find the derivative of, what's another one we found? Of minus 2 radical x. Then that's just minus 2 times the derivative of radical x. So the derivative of a constant times a function is just the constant times the derivative of the function. So in other words, you can kind of ignore constant factors when you're finding the derivative. Leave the constant alone in front, differentiate the function part, that will be the answer for the derivative. Second property, the second algebraic property of a derivative that is very important. The derivative of the sum of two differentiable functions. So if f and g are differentiable, I can add them together, I can subtract them. And it turns out that the new sum is also going to be differentiable. In fact, it will be the derivative of the individuals added together. The derivative of a sum is the sum of the derivative. The derivative distributes across sums. So you can factor constants outside the derivative, and you can actually distribute a derivative across sums. Derivatives do not distribute across products, and we'll deal with that probably next class. Now, why? Well, if I want to find the derivative of f of x plus or minus g of x, well, that's going to be the limit as h approaches 0 of f of x plus h plus or minus g of x plus h minus f of x plus or minus g of x over h. I'd be able to expand the parentheses and regroup. I'll be able to group the x's, the f's, plus or minus group the g's. And you can just work slowly through this and convince yourself that the sign distribution will be in fact what I just wrote down. But just skipping a step or two of algebra will ultimately get that. And then what happens is we will be able to split this limit, this fraction here. And hence we can split the limit. Limits distribute across sums, so I can find the limit of this one plus the limit of that one, and of course that just gives me f prime plus or minus g prime. The derivative of a sum is the sum of the derivatives. I can differentiate an addition of two functions by differentiating one at a time and adding them together. So that's how the derivative deals with constant factors and sums. So, quick example. The derivative of, say, radical x plus 1 over x, well, that's just going to be the derivative of radical x plus the derivative of 1 over x. It is going to be 1 over 2 radical x plus minus 1 over x squared, or you can just say 1 over 2 radical x minus 1 over x squared. I can just distribute the derivative across the sum. As well as if I have something like 5 over x minus 2x plus radical plus 6 radical x, let's say. Here I have a sum of functions and their constants in front. The first rule says I can ignore those constants and just differentiate the function part, which is the 1 over x and the radical x, and then just multiply them by the constant. I also know that the derivative is going to separate itself and do each of these separately. So this just becomes minus 5 over x squared minus 2 plus 3 over radical x. And eventually by like next week, actually, by Monday, I expect you to be able to look at something and be able to use the rules that we've already derived and tell me what the derivative is without going through the limit definition. You should definitely know the limit definition, but we're segueing from being able to need that, right? So the constant factor rule and the sum rule, which are the two rules, properties 1 and 2 respectively, allows us to take derivatives of more complicated functions. I can factor constants off, and I can actually distribute a derivative across the sum. So once I know the derivative of the individual functions, I can find derivatives of their sums and any constant times those functions. The derivative behaves a little wacky around products and quotients. We'll deal with that next time. But in the meantime, we're going to start with another very important rule. It's called the chain rule. Very important derivative rule. A lot of the other rules that we're going to learn, we are going to use the chain rule to derive those rules. It's a very important rule, very infamous, very famous. It should be a theorem. It's called the chain rule. This is the first shortcut we are going to be learning for finding derivatives. The chain rule, this tells us how to differentiate composite functions. It says, if f and g are differentiable at x, then the derivative of f of g of x, meaning if I plug one function inside of another function, the derivative is going to be the derivative of the outer function, leaving the inside one alone, times the derivative of the inner function. This is the chain rule. It is something that we know now. If I ask you on a quiz to regurgitate that rule, you should be able to write it down. This equation gives us the chain rule, assuming f and g are both differentiable functions. So, an example. Let's do an example. Why not do an example? Let's say, so for example, if someone were to ask you to differentiate the sign of radical x plus 1 over x. So So this is a composite function. There is a function. So here, notice that your f of x is like the sine of x, and your g of x is like the radical x plus 1 over x, which means that your f of g of x is going to be the sine of this. So when you're looking at something like this, you're actually looking at a composite function. You have one function plugged inside another function. The chain rule says to differentiate this function, what I'm going to do is I'm going to differentiate the f, leaving the g alone initially, then multiply that by the derivative of the g. So it's the derivative of the outer function times the derivative of the inner function. So this is going to be equal to the derivative of the outer function. Derivative of sine x is cosine, right? So the derivative of a sine is cosine. Cosine of what? Well, the original g. The original g is this, so I'm going to leave this alone first. Leave the inside alone initially. A lot of students forget to do that for some reason. Differentiate the outer one, leave the inside one alone. Right? So you differentiate the outside function. Then we are going to multiply by the derivative of the inside function. Now the inside function is a sum of functions, but the derivative of sum is the sum of the derivatives. What I do is just differentiate each one at a time. So this is going to be 1 over 2 radical x plus 1 over x. And that looks right? What's the problem?
Minus 1 x squared.
Is that okay? It's not okay.
Plus x squared.
I need parentheses. Students are going to mess up here, they're going to mess up with the parentheses. Don't be that student. Let someone else mess up. This thing it's going to be this times that entire thing. So if there are several things, you need to be able to distribute, right? You need the parentheses here. So now, I gave you a bunch of functions to play with. Go home, practice a few, plug them inside of each other, add them together, multiply them by constants. Create random functions that you want, and just go through the exercise of finding the derivatives of them. You can go to Wolfram, type them in, derivative of this weird thing I just invented, and it will tell you if you have the right answer, right? So go through different combinations of the things using composition, addition, and multiplying by a constant. I didn't teach you how, if you multiply two functions, what you actually do. There's actually that's a separate thing altogether. Now, you should be able to do that by Monday, because on Monday, all of this will be on the quiz. You need to know how to find the derivative by the definition. You need to know how to find the derivative of these functions that I mentioned, and certain combinations of these functions that I mentioned so far. Later on, we'll learn rules that help us to do this more generally for other functions, and how to figure out the rules for functions when we don't actually know what they are. But, proof of the chain. Let's end there. Why is this actually true? There are a lot of reasons why this is intuitively true, but since we only have 3 minutes, let's just actually prove this thing and be on with it. Again, chaining notation. Just to make it easier to write down. Call f of x, y, call g of x, u. So my f of g of x is actually my y with u plugged inside. Okay? So now we want to find dy dx. Remember, that's the Leibniz notation for the derivative. Now, dy dx is going to be equal to And again, I'm going to use some short remember, this is the limit as x approaches a of, say, y of u of a minus y of u of a over u of x minus u of a by the definition of the derivative. Again, that's going to be cumbersome. I won't actually rewrite this. Let's look at it as the denominator is the change of u, and it's going to 0 because the x is approaching a, and u is going to be continuous because it's differentiable. So fact 2 tells me that that's going to actually go to 0, and this is just the change in u. Similarly, by fact 2, this is just going to be a change in y. What I can do now is do that age-old, time-tested trick. I'm going to multiply and divide by something convenient. Sorry, dy dx, that was fine. I was looking here at dy du. We're going to need that eventually. We're doing dy dx. That's just the change in y over the change in x, which is this. But now, I'm going to multiply and divide by delta u, which is the change in u. That is going to give me the limit as delta u approaches 0 of delta y over delta u times the limit as delta u approaches 0 of delta u over delta x. Now, the first one, let me see pop that here. This is, sorry, I messed up with the u in the first place. So these are actually all x's. So you get me trying to rush through the chain rule. Chain rule should not be rushed. Okay, so that's delta x. Delta y over delta u times delta x delta u over delta x. Now, this guy here is u prime by definition. That's the definition of the derivative for the function u, right? Change in u over change in x as the change in x goes to 0. This one, though, this is going to be the limit as delta u approaches 0 of delta y over delta u. And this is by fact 2. I know that as the change in x goes to 0, the change in u goes to 0. I proved that in fact 2. And now, because the denominator of these changes is going to 0, that also gives us the derivative by definition. So this actually becomes y prime evaluated at u times u prime. And in other words, changing the notation back. The y, I called it f. So that's f prime. The u was what I renamed g. So that's g of x times the u prime. Well, that's just g prime. That's the chain. Now, with the chain rule, it's going to be so useful by the next class. Things are just going to explode. I'm going to use the chain rule to derive a bunch of other rules, and we're going to use those other rules to be able to differentiate almost any function you want in theory. We will get to that by next lecture. I will see you guys on Monday. And the quiz will be on all the stuff in this lecture, which is, we actually covered a lot of stuff actually. So, good luck studying for that. I will see you guys